Hello, good afternoon, everyone. Thank you for joining us. Today, we are going to talk about the concept of wireless power transfer, applications of this principle in healthcare industry, design challenges of a pacemaker, wireless charger, and modeling and simulation of a wireless power charger for a cardiac pacemaker using EMS for SolidWorks. Today from EMWorks team, my colleague Majdi El Fahem and myself Kal Dasroju will be presenting this webinar. Before discussing our today's agenda, let me introduce us. My name is Kal and I am working as an account manager for EMWorks. I handle commercial sales and marketing activities for our company. My colleague Majdi works as an application engineer and technical support expert. He is an experienced user of EMS and EMWorks 2D software and has extensive knowledge in low-frequency electromagnetics. Feel free to write down our details to email us afterwards for any inquiries. You can also connect with us over LinkedIn. Moving on to the agenda of today's webinar, I will be briefly discussing about our company EMWorks and the products we offer. Then my colleague will present the technical part of this webinar. At the end of the technical presentation, I will talk about various learning resources offered by EMWorks for its users. Now let us take a quick overview about our company EMWorks. We offer 3D and 2D electromagnetic simulation software as an add-in tool for SolidWorks and Autodesk Inventor 3D CAD. Our company was founded in the year 2000. We have a vast sales network in the form of 2 offices and a global reseller channel. We provide our solutions and services directly or through a reseller in America, Europe, and Asia Pacific region. Our company has a strong research and development team with years of experience in the field of electromagnetics. In addition, our products are gold certified by Dassault Systems SolidWorks Corporation since 2008. As you can see on the screen, we have 2 office locations. Our headquarters is in Montreal, Canada, and we have another office in Germany in Europe region. Now let us take a quick overview about the products offered by EMWorks. We offer 4 products with various add-ons covering a wide frequency range. Our first product is called EMS. This product can be used for electric and magnetic field modeling for low frequency applications. It covers many applications like insulators, cables, bus bars, permanent magnets, wireless charging devices, actuators, circuit breakers, transformers, and electrical machines. Our second product is called HFWorks, which is used for electromagnetic simulation of RF, microwave, high frequency and high speed electrical and electronic devices. It covers applications including wide range of antennas, resonators, filters, connectors, waveguides, etc. Our third product is called EMWorks 2D, which offers static analysis and covers simulation of planar and axisymmetric geometries. And our latest addition in the suite of electromagnetic simulation software is Motor Wizard. This product is a template-based motor design software. It offers analytical and finite element analysis of brushless DC electrical machines. In addition to these solutions, we offer few multiphysics add-ons like thermal, motion, linear statics, and circuits. In today's webinar, we will demonstrate how to model and simulate a wireless power charging device using EMS for SolidWorks product. Let's take a look at the licensing structure offered by EMWorks. We offer 3 different programs: commercial, academic, and startup. Each program has its own benefits and requirements. Within commercial program, we offer perpetual licenses, while in the rest of the 2 programs that are academic and startup, our licensing structure is usually annual based. As you know, the topic for today's presentation is simulation of a wireless power charger for a cardiac pacemaker. My colleague Majdi will cover various topics including concept of wireless power transfer, applications of wireless power transfer, design challenges of a pacemaker wireless charger, and simulating a wireless charging device using EMS for SOLIDWORKS. Before moving to the technical part of today's presentation, I would like to highlight few points. Kindly mute your microphones to avoid any background noise. You can use the GoToMeeting chat window to type in your questions and we will answer them at the end of this presentation. A webinar recording will be sent to all the registrants in few days. Now, I would like to request my colleague Majdi to take over and present the next part of today's presentation. Thank you. Majdi, over to you.
Thank you, Carl. Hello, everyone. I would like to thank you all for joining us today in this webinar. My name is Majdi. I am Senior Application Engineer at EMWorks, and I'll provide the technical part of this presentation. The agenda of our presentation today will cover the following topics. We will start by a quick reminder about wireless power transfer, same advantages and its main applications. After that, we will focus on our main topic, which is the use of this technology of wireless power transfer to charge a pacemaker battery. The particular advantages of this use will be highlighted. Later on, we will see the design challenges that can arise while building a wireless charger for an implantable device, and we will introduce our solution, EMS for SOLIDWORKS, and see how to overcome and solve these issues. An overview through few screenshots will give an idea about our solution. After that, we will study the different aspects of the proposed wireless charger using EMS for SOLIDWORKS. Before ending with a conclusion, we will have live demonstration of EMS for SOLIDWORKS in its environment. So let's start by a brief memory refresh about wireless energy transfer. Wireless power transmissions happens by creating an alternating magnetic field on the transmitter coil. That magnetic flux is then converted into an electrical current in the receiver coil. The generated electrical current depends on the amount of flux generated by the transmitter coil and how much of a percentage of the receiver coil is able to capture. The distance, the size, and the position of the receiver coil relative to the transmitter coil decides the coupling factor or coefficient of the two coils. Ever since the concept of wireless power transfer became popular, both scientists and engineers came up with various ways to realize this concept. These methods are classified based on the distance of transmission, maximum power, and method used to achieve power transmission. At the high level, we can find near and far field power transmission. Far field wireless power transmission is achieved by electromagnetic radiation, including microwave power and light power, while the near field transmission is established by electromagnetic induction laws. It includes several methods like inductive coupling, in which we will be focusing in this webinar. So, wireless energy transmission is widely used in many applications and fields. We can find them in our daily life, such wirelessly charging our smartphones and different types of wearable device like connected watch. It offers more flexibility like wireless reverse charging and also mobility. It reduces the use of cable and connectors and allows for charging a multiple devices at the same time. It can be used also to empower electric vehicle battery without any contact. research efforts are conducted to find an optimal way to use buried wireless charger in the roads. So electrical cars can be charged while they are operating. It's also used in charging and operating medical implants such as subcutaneous drug supplies, pacemakers, and other implants. Wireless power transfer, especially with high resonance, allows convenient continual charging of these implants without the need for frequent surgery and the inclusion of external charging ports. We can see here some examples of inductive coupling models are shown in this slide. We use EMS for SOLIDWORKS to simulate them. Different topologies of wireless charger used in electric cars can be simulated, and their specification can be studied using EMS. We have in figure 2A a wireless charger with aluminum and iron core used to charge electrical car battery. Tiny inductive wireless charger for smartphones also can be analyzed using EMS for SOLIDWORKS. Since health is one of the world major topic in nowadays, so we wanted to bring up an example that has a relation to this topic. Then in the remainder of this presentation, we will focus in studying a wireless power charger used for cardiac pacemaker. This technology of wireless power transmission has been used since 1958 to charge battery of pacemakers, but this type of pacemakers was left out for several reasons, like the process of charging that should be repeated each few days and a short service life of the used batteries at that time. Now, and thanks to the advance in technology, the interest of using pacemakers based on rechargeable batteries is renewed. This kind of pacemakers can help to reduce complications that can be caused by surgeries during pacemaker replacement. It reduces the risk of infections and improves the quality of life of the patient. However, this rechargeable pacemaker offers quite interesting advantages, but its wireless charger can represent some weaknesses like low efficiency and high power loss. And they may cause some high electromagnetic radiation, and this can lead to an electromagnetic interference issues, whether with the human body or electronic devices. So the design stage is crucial in building a wireless charger for implanted heart pacemaker. It should resolve the challenges and issues that can appear. In this context, we will find out how can EMS for SOLIDWORKS provide a complete solution to overcome the faced challenges when designing this system and help to create more efficient and suitable wireless charger for such application. Now let's talk a bit about the design challenges of a pacemaker wireless charger. So, the transmitter and receiver coils design have an important influence on the wireless charger output voltage. The performance of the wireless charger depends highly on the air gap length and the different misalignment of both coils. These parameters can affect the coupling coefficient between the primary and the secondary coils. The efficiency of the system can be determined depending on different factors like the input and output powers and electromagnetic losses. The electronic circuit of the wireless power system should be analyzed as well to see the impact of different loads on its function. It helps also to analyze the wireless charger under the resonance condition. Electromagnetic radiation should be restricted around the human body because it has many side effects. The shielding has a great impact on the wireless charger. For this reason, it should be also carefully studied. To cover these design topics and issues, we propose our solution, which is EMS for SOLIDWORKS. EMS is an electromagnetic simulation software fully integrated inside SOLIDWORKS. It has also few multiphysics capabilities. It helps us to study the different geometrical arrangement and design scenarios of the studied wireless charger coils using multi-configurations and parameterization features. EMS came with an embedded circuit simulator that can couple FEA analysis to external circuit, giving more electronic components options and more realistic results. AC harmonic and transient magnetic simulations both can be performed using EMS for SOLIDWORKS. Electromagnetic losses and SAR can be computed and generated by EMS. The coupling to thermal can be defined within the same magnetic study, so no import or export of data in case we want to see the heat generated by the eddy losses and the shielding parts. Let's have a quick look on EMS environment through these snapshots. And at the end of this presentation, we will go to check live EMS inside SOLIDWORKS. As we mentioned earlier, EMS is an add-on inside SOLIDWORKS. They both have same look and feel. Once EMS is added to SOLIDWORKS, its tab will appear in this top menu. This screenshot shows the property page when a user clicks to create a new study. We can see the different study options. We have 6 modules, including 3 magnetic modules and 3 electric modules. Parameterization feature can be enabled through this page also. It helps to parameterize whether geometrical or simulation variables. At the left, we can see the multi-physics options of EMS. EMS provides few and great multi-physics solvers like thermal, linear static, and mechanical motion. In addition to these solvers, we have the circuit coupling features. After creating a study, EMS3 is generated. It is a simple and a compact structure. It has a simple and a compact structure. We can see the different sections in front of us. Nothing is hidden. From the top to the bottom, we can find the materials section. Simply right-click at one or more components to apply a material. A rich and well-organized material library is shown at the right side. User can also add or customize his materials inside this library. Some properties like pH curves, temperature-dependent properties can be imported easily from text or Excel files. Below the materials section, we have the loads and boundary conditions, where we can define coils, excitations, and so on. Under the section, it came as the meshing step. EMS is equipped with a flexible and advanced meshing tool. Also, it is possible to apply mesh controls to define or to specify mesh size in specific surfaces or bodies. And finally, after solving a study, a results section is created. It groups both tabular and 3D results folders. EMS has several post-processing options which make the results exploring much easier and more efficient. So after having an idea about EMS for SOLIDWORKS, we can move on now to study our wireless charger system for a pacemaker. We are going to start by the impact, or to see the impact of the relative position of the charger coils. Both the transmitter and the receiver positions play an important role in the performance of any wireless power system, not only this for this case, which is the implantable devices. It affects mainly the coupling coefficient, which also has a great impact on the receiver output voltage. When the diameters of wireless charger coils are big enough compared to the air gap between both of them, the coupling is considered tight and the efficiency of the system can reach maximum values. While in the opposite case, a big amount of the magnetic field transmitted by the primary coil won't reach the receiver coil. Hence, the induced back EMF will be small. In addition to axial air gap, the relative or the distance between both coils, the relative position of the transmitter and the receiver coils can have lateral and angular misalignment. All of these situations will be studied and discussed in the upcoming slides. Now we are going to see how the axial air gap can affect the different parameters of the studied wireless charger. The studied wireless charger is shown in figure 4a. It is made of two coils with the same dimensions. Each coil has 10 turns. In addition to coils, the system has in both sides aluminum and iron cores for shielding purpose. The initial air gap distance is 15 mm. The parameterization feature of EMS is used to sweep the air gap distance. The simulated air gap distances are illustrated in figure 4. After running all the air gap distances, we collected the wireless coils parameters calculated by EMS. Self and medial inductances results 5. The three inductances results decrease when the air gap gets larger. Same behavior can be seen for the AC resistance from figure 5b. The results of the coupling coefficient K calculated by EMS are plotted in figure C. It also decreases when the air gap increases. To make things clearer, the magnetic flux density plot versus different air gaps is shown in figure 6a. It can be seen that less magnetic field can reach the receiver coil when the air gap distance increases. This explains why the induced back EMF in the receiver coil becomes smaller with the air gap as shown in figure 6c. It shows that when the air gap is only 5 mm, the receiver voltage reached a peak value around 4 volt, while it is less than 0.5 volt when the air gap exceeds the 20 mm length. So as a conclusion, we should keep the air gap as minimum as possible, but this depends on several factors like the depth of the implanted receiver inside the human body. In addition to the axial air gap, when we have two contactless parts, it is expected to not have a full or a perfect alignment between them. So some lateral or at the same time, angular misalignments can be obtained between the transmitter and the receiver coils. So let's see first the impact of the lateral misalignment. Medial inductance and coupling coefficients results versus lateral distances between the axes of the primary and secondary sides are plotted in figure 7b. Both curves show similar behavior like we have axial displacement. The medial inductance and hence the coupling coefficient, both of them start to decrease when both axes of the coils are no longer collinear. The flux linkage of the secondary coil behaves the same as can be seen in figure 7c. As we have done for the axial air gap, we can see the magnetic field distribution versus different distances. It is clear that the magnetic flux is not able to fully reach the receiver when the axes move away. Hence, it's obvious that the induced voltage in the receiver is going to be smaller when the distance becomes higher. Now we are going to see the impact of the angular deviation between both transmitter and receiver coils. Angular deviation means that the facing planes of the primary and secondary coils are no longer parallel. A small increase of the medial inductance and the coupling coefficient can be noticed from figure 9a. The magnetic field going from the transmitter to the receiver keeps the same or maybe higher values for the simulated configuration. This can be confirmed from figure 9b. No big variation in the magnetic field of the receiver. The induced voltage translates this behavior by going a few steps up. Now let's move to see the impact of the frequency on the wireless charger performance. So the frequency has several effects on the wireless charger system. A frequency sweep analysis is performed using EMS inside SOLIDWORKS or for SOLIDWORKS to study the different aspects of this impact on the wireless charger. Figure 10b shows the coupling coefficient, which is decreasing with the frequency. So we may expect that the induced voltage also will decrease. We will find out in the next slide. So as we said, however, in the previous slide, we have seen that the coupling coefficient decreases with the frequency, but the induced voltage of the receiver has different behavior. It increases when the frequency becomes higher. The voltage is directly proportional to the frequency and has greater impact than the coupling coefficient. So now we can get higher induced voltage by increasing the frequency. But on the other hand, higher ED losses will be generated in the shielding component, which means we will need more power because the efficiency will be reduced. As can be seen, the ED losses shown in figure 11b are increasing versus frequency. So let's suppose that we can remove the shielding components. Another limitation of using very high frequency in wireless rechargeable and implantable device is related to high risk of electromagnetic radiation in the human body, and this we will study. We will be studying this in the end of this presentation. So from these figures, it can be seen that the magnetic field is much more concentrated and directed to the receiver coil when the frequency is high. Another way to improve the efficiency of an inductive coupling system is by using a resonant circuit. This technique allows to increase the transmitted energy even when the coupling is weak. This goal can be achieved by having primary and secondary operating coils operating at the same resonant frequency. Two series resonant capacitors should be added to both the transmitter and the receiver circuits. The capacitance value of each capacitor is using the resonance formula. This formula contains the resonant frequency and the inductance of each coil. This is why the inductances of the coils must be accurately calculated. We can see from figure 13b a good agreement between EMS results and our reference results. These parameters are computed at a frequency of 20 kHz, which will be used as a resonant frequency. EMS coupled to circuit is used to create the simulated resonant circuit and run the simulation. It's clear from figure 14 that the resonance has a great impact on the wireless output data. We can see that at the resonant frequency, which is 20 kHz, both induced voltage and the current of the receiver are too high compared to the rest of the frequencies. Now we're going to have an idea about electromagnetic compatibility and specific absorption rate. For implanted and wearable medical devices like pacemakers and also wearable devices, like pacemakers and phones, the electromagnetic radiation should be limited as much as possible and not exceed the EMC standards limits established by international healthcare organizations. Therefore, we have simulated the wireless charger system in realistic conditions. We have used a human body where we have put the receiver. Both the transmitter and the receiver operate at the resonance to have maximum transferred power. The human body has very low conductivity, but it increases with the frequency. The simulation were performed at two resonant frequencies, which are 20 kHz and 1 MHz. Figure 15a and 15b show the magnetic field distribution inside and around the human body. It can be noticed that the field is stronger and covers larger area at the frequency of 1 MHz. ED losses density generated in the human tissue reaches a value of 0.5 watt per kilogram in case of 20 kHz, while it is much higher when the frequency is 1 MHz. ED current is proportional to the frequency and also the electrical conductivity, which increases also with the frequency. The calculated SIR values show a higher rate when the frequency is 1 MHz, while it is small when operating at a frequency of 20 kHz. This is give us an idea about the SIR and how and the limits of this quantity. Now let's investigate another factor that can affect the efficiency of the wireless power system. Shielding has an important impact on the magnetic field strength and orientation. We can see the difference in the magnetic flux plots in the 4 figures of this slide. The magnetic field is symmetric around the transmitter coil. An important field is in case of a wireless power transmitter without shielding. An important field is linked to the air, so the coupling is weak at this situation. When the aluminum plates are added, a low field is now oriented to the receiver coil. Since the air gap is a bit high, the field couldn't reach the secondary coil. The field became stronger by adding the iron cores. Having both aluminum plates and iron cores makes the field stronger and well conducted to the receiver coils. A smaller amount of the magnetic field is linked to the air now. This helps to reduce the power loss, protect a human body and electronic device from electromagnetic interferences, increase the coupling between both sides of the wireless charger. It's clear now how is the impact of the shielding on the magnetic fields. The field is well concentrated in small region around the wireless charger in the presence of the shielding, while it propagates in a larger area when the shielding is removed. But as we have seen earlier, the shielding may result in higher ED losses when the frequency becomes high. Now we're going to have a quick and live demonstration of EMS for SOLIDWORKS. So EMS, as we said earlier, it is fully embedded inside SOLIDWORKS. So they both have the same look and feel. We can move from SOLIDWORKS model to EMS tab by clicking this icon. We can find here the assembly. We can just right click. We can use the first option to create a study. A property page will appear as a pairing. So we have now the studies options. So we have 6 options. We have magnetostatic, AC magnetic, transient magnetic, and the 3 modules for electric simulations, which are electrostatic, electric conduction, and AC electric. We have some settings, so some factors. We can use symmetry. So here we have an axisymmetric model, so we can run only portion of this model using, and we specify the symmetry factor, then the results will be automatically computed. We can enable the parameterization feature. This feature helps to parameterize both geometrical and simulation variables, and also additional options here. Now we can move to the next tab, which contains the coupling options. Just let me switch to this one. So we have thermal coupling. We can couple our magnetic or electric studies to thermal, to structural, or to both of them. Then we can couple our electromagnetic or magnetic simulation to motion, to SOLIDWORKS motion. And this is what we use the coupling to circuit in our simulation to simulate the resonant circuit, for example. So after creating a new study, so EMS3 is generated. Now from the top to the bottom we have the material list, so we can easily apply material. So we have 3 options. We have favorite materials and recent also applied materials. So we can select materials from these options. So just let's try by applying materials. So we have this is EMS material libraries. It's well organized and contains several materials, and also the user has the possibility to add or customize his materials. So let's see how here is the option how to define a coils. We can define whether solid or wound coils by simply click. So we choose this coil. We can define entry port. Select the face. It's the entry, and it is since it is a loop, since it is a coil, so the entry will be the same, the exit part. So, and here we can define, we have more options. We have the number of turners, the diameter, the conductor diameters. We have the filling factor also. It can estimate the amount of copper inside this coil, and we can define whether it is current-driven coil or a voltage-driven coil. So we have already created or solved 2 studies with parameterization. Let's take a look at the parameters. This is the design scenarios. So we have here some parameters, some variables. We can add some simulation variables also. Here the solved parameters, the solved scenarios. So we have different air gaps. So here, and by we run all these dimensions within the same study. So yes, the results section, the results table. So contains inductance, current, flux linkage, impedance, resistance, coupling coefficient, and more results like losses and voltage and so on. So we can check the coupling coefficient. So I have this is this is the coupling coefficient of the studied system. It is high when the air gap is small. This is the air gap when the air gap is 5 millimeter, and this is when the air gap is 20 millimeter, for example. Became smaller. So let's have a look at induced voltage. We can plot real, imaginary, or the magnitude, and here is the induced voltage. So different 3D results are allowed by EMS, so we can see different options of plotting. So we have section and isoplottings, vectors, fringe plots, lines, and streamlines, points, and so on. So just let's open this. Show. So here we can see the magnetic flux that goes from the transmitter to the receiver. So the transmitter is at the bottom and the top coil is the receiver. So we can animate this plot and see, can animate versus phase or scenarios, time, if we are running time simulations. So now we will do the animation versus scenarios. It is clear that the magnetic flux became smaller when the distance between the 2 coils increases. So as you can see, the red zone is just around the transmitter, and it doesn't reach the receiver coil. So on side, we can have vector plots also. Okay, we can see the vectors that goes from vectors that go from the transmitter coil to the receiver. And this is so. Let's see now the circuit. I have this is our schematic. Here is our source, sine wave source, and we have the coils, our winding, and this is the resonant capacitor. The resonant capacitor, this value is computed using the resonance formula, and also here the receiver circuit. So we have a load of 1 ohm, a resistive load of 1 ohm. You can check the results and see, for example, the current. So the input or the transmitter current is around 8 amps, 8 amp peak value, and the receiver is around 2.3 amps. So this is at the resonance. You can see. Have a look at the vector. We can also check, okay, can also couple this simulation to thermal and see if there is enough losses that can generate some heat and the shielding parts. So let's go back to our presentation. Okay, so now we reached the conclusion. So the use of wireless charger for pacemaker has several advances, like reduction of infection risk and surgeries complications. We have seen in this during this webinar that our solution, which is EMS for SOLIDWORKS, which covered the different design issues posed by this wireless charger, and it is specified and used for implantable devices. We studied the impact of coils positions on the wireless charger performance. We swept the frequency and determined its effect on the outputs of the wireless charger. Also, we simulated the charger under resonant condition, which helped to study or estimate the high amount of energy, transmitted energy from the transmitter to the receiver coil. And we investigated also the electromagnetic compatibility, and we calculated the SIR, which are two important quantities for such application. At the end, we analyzed the shielding effect of this charger. Thank you for your attention, and I hand over the screen again to my colleague Carl to continue the presentation. Thank you.
Thank you, Majdi. We used EMS product to simulate a wireless power charger. Now let us take a quick overview on this EMS software. As I have mentioned before, EMS product offers electrical and magnetic solvers. In addition, few multiphysics add-ons are available with this product, like thermal, motion, linear statics, and circuits. EMS software is available in 4 package options: electric package, magnetic package, professional, and premium package. To get more information on the software packaging and pricing, you can connect with me after this webinar. To design a wireless power charging device using EMS software, magnetic package with circuits add-on should be used. Other optional add-ons can also be utilized, like thermal analysis, if required. As you can see on the screen, this slide represents a small subset of capabilities available in our EMS software product. To design a wireless charging device, 3 capabilities are highlighted and utilized in the product demo you saw earlier. Number 1, parameterization. This capability enables a designer to parameterize any SOLIDWORKS dimension or simulation parameters to run multiple what-if scenarios and determine a best design. Number 2 is circuit analysis. Through this embedded circuit editor capability, a user can drive AC magnetic and transient magnetic study through voltage current sources, RLC components, and switching devices. And finally, AC harmonic and transient magnetic. These solvers can help a user to analyze magnetic fields, forces, eddy currents, losses due to time harmonic and time varying currents. Now let us do a quick recap on EMWorks products and their related applications. We can divide EMWorks offerings into 2 categories: applications related to low frequency simulation and applications related to high frequency simulation. Within low frequency category, we offer 3 products: EMS 3D, EMWorks 2D, and Motor Wizard. And these products can be used to design and simulate applications like cables, insulators, bus bars, magnet arrays, eddy current braking systems, wireless charging devices, transformers, and electrical machines. Within high frequency category, we offer one product known as HFWorks. This product can be used to design and simulate high frequency applications like antennas, waveguides, filters, resonators, connectors, etc. With regards to learning resources, we offer various free learning resources. With the software purchase or an evaluation license, users can access the demo viewer section of the software, through which they can access many predefined model examples and tutorials. In addition, we post application notes, blogs, and videos on our webpage and social media channels regularly. We also offer paid customized training sessions to all the users of EMWorks software. Anyone interested to get more information on our products, including a trial license, quotation, can go to our Contact Us page on EMWorks website, select the appropriate category and submit your request. One of our representatives will reach out to you soon. Before we answer your questions, I would like to thank you all on behalf of EMWorks for participating in this webinar. Feel free to contact us after this webinar to get more information on our products. Thank you.